Let's get the recording going. And let's get our PowerPoint going. Okay. Oh, and the computer is choppy. So we are taking a note here. Okay, so our second unit is on light and optics. All right, and this is our physics unit. And this again, physics is the study of the way matter and energy interact. Are you not going with any paper? You're going with a paperless? I could give you a piece of paper and a pencil if you'd please. You're going to give it a shot? Okay, all right. All right, that's excellent. Again, physics is the study, could you take your hat off, please, Eric? Physics is the study of the way matter and energy interact, all right? Chemistry, to contrast that, is the study of the way matter interacts with other matter and the changes it undergoes. So we saw all kinds of examples of chemical change in that last unit, because when we mixed those compounds together, their atoms rearranged and something new was formed. When it comes to physics, typically we're not talking about something new being formed. We're just studying what is happening as we put some energy into something. What does it do? All right. So we're talking about light and optics here. Another type of physics that, if you continue on and maybe take the grade 12 college physics, is something called kinematics, and that's the study of motion. So I'm just trying to give you a sense of what else is involved in physics. So kinematics would involve talking about things like a car going down the road and how much force you're pushing it as you step on the gas pedal from the engine and how it speeds up and slows down. So again, we're adding energy to something like the car, and the car speeds up and it slows down and it does all kinds of things. So that's called kinematics, all right? You can talk in physics about electricity, and that would be putting some electrical energy into a wire or maybe into a light bulb and having that electrical energy do something. It causes electrons to move. And again, the matter is moving, the matter is doing something in response to the energy, and the study of that is physics. Notice how in all of these situations, the matter doesn't change. The car is still a car when it's done speeding up and slowing down. The wire is still a wire after the electricity has gone through it. But it does something interesting when we impart some energy into a system like that. So another type of physics, and I'm trying to think of even more of them, sound itself, right? Sound is a study that we study waves in sound. So when something vibrates, it can create a sound wave that propagates through the air. Right now, my vocal cords are vibrating. That's causing the air molecules to vibrate. Those vibrations are traveling through the air. They get to your ear. Your eardrum vibrates in response, and then ultimately we hear it, right? That's another aspect of physics. So the physics that we're looking at is the physics of light. So we want to talk about what light is. That's what we're going to be doing today. We want to talk about how light travels. We're going to talk a little bit about that tomorrow. And then we're going to be interested in what happens to light when it encounters an object. What happens to light when it runs into something, all right? And there are 3 or 4 different possibilities that can happen when light runs into something. What do you think? What do you think one possibility of it is when light runs into something? Yep. It can bounce off. We call that reflection, and we're actually going to be studying that first after we talk about what light is for a couple of days. So light can be reflected off of something. Yep. It can go through it. We call that transmission, all right? If I've got something like a piece of glass or perhaps like water, a transparent colorless liquid, then that light can go right on through it. You guys, this is pretty good. There's actually only one more option that can happen to light. It either can bounce off of it or go through it, or one other option, yep. It can be absorbed by it, which is stopping it, correct. It can be absorbed by a substance. And you probably have experienced that if you've worn a black jacket or a black sweater on a nice sunny day. You go outside and all of a sudden you can feel that. And that's because all of that light is being absorbed by that sweater, turned into heat, and then you're sweating bullets because you've absorbed that. Correct. Those are the 3 things that the light can do. And we're going to be looking at each of those 3 things. reflection, we're going to study mirrors, right? So we're going to study what happens when light hits mirrors and how do we get a nice perfect image of, say, our face or an object in a mirror. How does that happen? What is happening there? Transmission, we're going to learn about lenses, right? So if you wear glasses or have contact lenses, how do these lenses help me see things that are nice and close, right? So how does that work in aiding my ability to see? So that's the thing that we're going to look at as well. And then at the end, absorption, or the absorption of light. And that manifests itself as colors. So when we look around the room and we see various colors, it means some of the light's being absorbed, but some of the light is being reflected, and ultimately in our eyes we get a perception of what that color is. So this unit is going to cover all three of those aspects. All right, so to start with today, we just want to talk about what light is, all right? And you can write that down. We want to talk about what light is and how this light can then behave in slightly different ways. So before I get going on writing down what light is, I want to show you a couple of things here, all right? I'm going to show you all kinds of stuff by the end of today's lesson. That's why I don't know how well this is going to translate into a video. You've probably seen one of these things before, all right? What is that? Does anybody know what that is? It is a pith ball from good old grade 9. I'm going to get these things out of the way. It is a pith ball from good old grade 9. So I'm going to get here a little bit of the good old rabbit's fur and get an ebonite rod. I might even get a positively charged rod as well. It doesn't matter. And I'm hoping this works because if I take that charged rod and I charge it up, I'm hoping it will repel. But you know what? It's not charging very well today. And that's because of probably some of the humidity that's in the air. It's going to start raining, I think, later on today. And when the air is humid, it's very difficult to build up a static charge. So let me try it with this positive one. We're going to just give it a shot here. I'll rub this with the plastic bag. Oh, and there you can see I've got a stronger charge there. So right now you can see it's attracted to it. And I could make that positive and have it repel and do all those good things that you did in grade 9, but I'm not interested in that aspect of it. I'm just interested in the fact that there is a force of attraction. I'm not interested in the fact that it's attraction or repulsion. So let's take this rod and let's have it attract. There it is right there. You can see it attracting right there. Now, if I take the rod itself and I wiggle the rod around, actually, let me put it this way, and I start wiggling the rod. Isn't that fun? Isn't that neat? It's almost like magic. If I had kids here that you know had never taken grade 9 science, they'd think I was magic. Isn't that great? That's a great thing. So that's pretty awesome. I can take a charged rod and without physically touching the pith ball, I can make the pith ball move. That's fun. Now, you guys look a little bored here. I even just have a yawn coming across right now. Why are you not surprised by this? Why does this not say, whoa, Mr. Sanders, you're magic, it's awesome. Why aren't you surprised? You already knew that from the grade 9. Excellent, that's good. Now, let's think about what's happening here. Let's think really critically about what's going on. Something is making that thing wiggle around like that. Something is taking the energy from my hand here and putting it into that ball. So the energy is being transferred from my hand into that ball. How is that happening? How is it getting there? How is that energy going from my hand to that ball? What do you think? Nope, there's no electrons moving through the air. So the answer to that is no. The attractions. So what are these attractions? What is it that's actually making that energy go to the other side? They're opposite charges, they attract, but what is the thing that's making the energy go to the other side? That's the whole crux of this thing. What is it? What is going on in there? It has to do with something called fields. Now, it's not a magnetic field because those aren't magnets. I could do the same thing with magnets, but I'm not using magnets. I'm using electric charges. So it's not a magnetic field, but what kind of a field is it? He's reading ahead. These are electric charges. So it's not a magnetic field, but it's what we call an electric field. Let me draw it on the board. You do not have to draw this. So what we have is, we have a thing that is charged. And I'm going to draw the rod here like this, and I'm going to put some pluses on it. All right? And then I have a pip ball. And in this case, I'm going to change my pip ball. I'm going to imagine that I have a pip ball. Instead of on a string, I'm going to imagine that I have it on a rod that does not conduct, but the pip ball can move up and down. And if I move my ebonite or my plastic rod up and down, what will the pip ball do in response? Move up and down. Now, the reason it moves up and down has everything to do with something called an electric field. Michael Faraday in the mid-1800s was the first to imagine this electric field. He was a very not typical scientist of the day and had a great imagination. So he imagined that there were invisible lines coming from charged objects, all right? And he called these invisible lines electric field lines. And he imagined that between two objects, they would be connected by one of these invisible lines. So when we wiggle the rod, Faraday imagined that the line, the electric field line, also wiggled. Now, my question to you, and you saw the demonstration there, if I did that up there on the board, when I move the ebonite rod or the charged rod up, we all know that the pith ball would move up. My question is, does it move up simultaneously? Does it move up at the same time? Or is there a delay in the movement? There is actually a delay, not for the same reason as this. You saw it kind of delaying. This has to do with the momentum of the ball, but there is a delay. So Faraday imagined that when you wiggled something that was charged, you put a wiggle in the electric field line, kind of like when you wiggle a rope or a garden hose. You know what I'm talking about? You send that wave down there. So when you wiggle a charged rod, you're putting a wiggle in the electric field, and that wiggle travels down until it gets to another charged object, which then can catch the wiggle and absorb that energy. Well, it turns out, and Michael Faraday's friend, an older friend who was actually about 50 years after him, but they did talk to each other, a guy by the name of Maxwell discovered what that wiggle was in the electric field. And that wiggle in the electric field is what we call light. So when an electric field wiggles, we have light. Now you might be saying, Mr. Sanders, I saw you wiggle that charged thing over there. I didn't see any light, so I think you're crazy. There's no way you were producing light. Now in actual fact, I am producing light, but I'm producing light at such a slow wiggle that our eyes can't see it. So as I wiggle this, it wiggles. That is so much fun. Do that too. I am producing light, but the wiggle is too slow. The light that we see has to be incredibly fast wiggles in electric fields. Yep?
Like kind of how the taser, like it creates light between the two.
No, the taser is an electric arc. I'm going to produce an electric arc in a moment, and I'm going to show you what that looks like, not for the reason of a taser, but that's not the same situation. I'll talk about how the taser produces light in a moment, okay? So we can't see this light because the wiggles are too slow. We need the Wiggles. The Wiggles, isn't that great? There used to be a band called the Wiggles. When you were kids, did you ever watch the Wiggles? on CBC? No, the Wiggles?
Still,
There still is. I'm glad some people know who the Wiggles are. So if the Wiggles are fast enough, we can see light. So right there in those lamps, there are electric charges wiggling phenomenally fast. That's causing a wiggle in the electric field. You can't see the field because it's an invisible field. They're entering our eyes. In our eyes, we have cells that behave like the pith ball, that have charges on them. They're incredibly small. We don't have pith balls in our eyes, by the way. They just behave like the pith ball. So when those wiggles enter our eyes and hit the cells at the back of our eyes, those things wiggle. They send an electrical impulse through our nerve. It goes to our brains, and we see the light. Do you see the light? Can you see the light? I feel like an evangelist. Do you see the light? Okay. All right. So how fast would I have to wiggle this to be like the light? Well, I'd have to wiggle it phenomenally fast. I'd have to wiggle it, and I'm going to have to use some scientific notation. I'd have to wiggle it 10 to the 14 times per second. What does 10 to the exponent 14 mean when it comes to zeros? It's not the speed of light. The speed of light is different. Be careful. It's counting the number of wiggles. That's different than the speed of light. How many zeros is on the back of that number? 14. That's a lot. That's a lot. So I would have to wiggle this that fast. I can't actually wiggle it that fast. I can't do it. If I could, and I charged it, and I could go 10 to the 14, would it look white? I have no idea. I can't actually do that. See, I contest that Hogwarts is not a school of witchcraft. It's a school of physics. So the way they produce the light, see what Harry Potter does when he takes the wand out of his cloak? He goes like this. You just don't see it. And then he goes, Lumos. Nothing? You don't watch Harry Potter? Oh, okay. No? Not a school of physics? Think about it. Here, let me show you another one. Here's another one. Accio water. See? See how I did that? Did you see that? Huh? I didn't go to Hogwarts. I just went to university. Accio water. I tell you, you think about it, Hogwarts is not so cool. Anyway, okay. So, I've distracted you. Back to the original story. What is light? Whenever a charged object wiggles, its electric field gets wiggles, and that is light. In order to see the light, you need to have something that can receive that wiggling field. In this case, the pith ball was seeing the light that I was producing. It had the right characteristics in order to receive that wave. For the light that's coming from our lights, there are charges, electrons wiggling in there. It's causing a ripple through the space. We catch it in our eyes. It hits those cells at the back of our eyes. They wiggle, and that sends an impulse through the nerves, and we see the light. Yep. No, not necessarily. So I'm going to get you to write this down. Whoops. Just write down that it is a wave of electric and magnetic fields. No. That is a secondary nervous response to the brightness of the light. All right? And you know how sometimes when you look at something really bright, like when I showed you burning magnesium, how you could see that background image kind of for a while? That's also biological responses to the light, and I really don't know how they behave. I just know that there has to be these things in our eyes that receive that. Okay, so what is light? Light is wiggling electric or magnetic fields. I've given you the electric example, and it propagates as a wave through space, and in order to see the light, you have to have the proper instrument that can catch those wiggles. So, some light, as you saw here, is invisible. We can't see that light because our eyes are not the proper detectors. But some lights are visible, the lights that we have that illuminate the room. So what I want to talk about now is, no, we're not worried about that, is the electromagnetic spectrum. And I am going to ask you to write that down, but I'm going to put it on the board for you and show you how I want that written. You might think, whoa, that's a lot of information right there. But write down the title, write down what the spectrum is, and then I'm going to draw that on the board for you. And if you're like Max and you're trying to type in the notes, you can make reference to the PowerPoint, right? Because remember, the PowerPoint's online, hey, Max? So you can always go back and look at that. So the way I want you to draw this, and actually, you know what? I'm going to get you to flip the whole thing over, because I like to have the shorter wave, or sorry, I like to have the longer waves on my left-hand side. So we're going to draw this picture, and I'm going to start over here, and I'm going to just put a line across here. We're going to do that, okay? All right? So I'm going to guide you how I want this. And the first type that I'm going to put down here is AC. All right? AC. And the meters are very, very long. I'm going to, let's just put down here that these are long waves. All right? In other words, the waves are really long waves. Okay? It's caused by slow wiggles, very long waves caused by slow wiggles. And this is low energy. It does not take a lot of energy to make these waves. Now, AC stands for alternating current. And in a moment, we're going to write down in a little bit of a note on where these things are formed and some uses for them and where we might see them, okay? So the next one we're going to put in here is, and you can see there's a whole bunch of them in there, and I'm going to put a line here. Yeah, we'll do this right here. I'm going to put here, and I'm going to put another line in here. Sorry, radio. Radio. AC, then radio. All right, this little short line here is what is in the middle. That's my visible part that I want to talk about. But AC and then radio. Radio waves. Radio waves that you use in the car when you pick up a radio signal. All right? Radio waves are long waves, and they're not very energetic. Right? They can't get into the house sometimes. You lose your channel. Or perhaps if you're in the city where there's lots of buildings, you lose the channel because they can't get around very well. They're not very energetic. Next, we have here, oh, I do have to put one more in here. Sorry. I got to put one more in here. Radio, and we have microwaves. Microwaves. Now, microwave oven, all right? Now, the microwaves that come from a microwave oven are a specific type of microwave, as if it's a specific color. So it's not that any microwaves would fry your brain or fry or cook whatever you're cooking. Only certain microwaves do this. So the microwaves in microwave ovens are very specific. Now, I will tell you that in between radio and microwaves, there's a little thin sliver, cell phones. Cell phones actually they send their messages with a certain type of microwave. Now that concerns some people because what do they say? What do they say about too much cell phone usage? Blah, 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 blah. What do they say? Could mess with your brain, give you tumors, and blah, 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 blah. Why? Because the people that say that say, well, this is producing microwaves, so you're frying your brain with the microwaves, and it's causing tumor and it's causing cancer. But the microwaves in this are not the same as the microwaves from a microwave oven. You cannot hold that in front of your glass of water and heat it up. It doesn't work because they're not the right color of microwaves, okay? And each phone has a slightly different frequency, and that's how the phone companies know how to contact you with each different little color of the microwave. So some people say, that's hogwash. It's a low energy wave. That low energy wave doesn't do anything. Do the radio signals hurt you? No. Could you take the headphones out, guys, please? I do want you to pay attention. No, they don't. So some people say, no, it can't hurt you. Some people say yes. Yep. Careful with the term radiation. All of this is radiation. This is all electromagnetic radiation. The term radiation simply means energy emanating from something. So that lamp right over there, that light bulb that we can see in the field ceiling, is producing visible electromagnetic radiation. So you got to be careful. When you say radiation, you mean bad radiation, all right? And we will talk about bad radiation up here in the high energy part, but this radiation, other than you don't want to be affected by a microwave, right? Because that can be harmful for a certain reason. Other than that, these are pretty tame, right? You can be hit by a radio wave, it doesn't do anything. So microwaves are a different color than cell phones. Okay, let's keep going on this. IR, which stands for infrared radiation. Does anybody know what infrared radiation is also called? It's a very common term. If you have thermal, correct, thermal. Or how about an even simpler term than thermal? Heat. It doesn't have to be red hot, it just has to be heat. Anything that's warm is giving off infrared radiation, which is why when you have infrared goggles on, you see things that are warm, that are giving off heat. So infrared is heat. Excellent. In here, we have visible, and I'm going to blow it out here for a minute. This is the visible. The visible part of the spectrum. This is what we can see. These are the colors of the rainbow. And it starts here at low as being red, all right? And then we go through the spectrum. Roy, G, Biv. Everybody hear of Roy G. Biv before? That's how you can memorize the colors of the rainbow. What do they stand for? Green, blue, indigo, violet. And I didn't separate it out enough. It doesn't matter. Roy G. Biv, when it comes to their waves, actually, let's not worry about the wavelengths. I was going to put them in there. But again, this is lower energy. And this is higher energy. Okay. That's the colors that we can see. A tiny little sliver in the electromagnetic spectrum. A tiny little sliver. That's what our eyes are tuned to see. In order to see the rest of them, we need other equipment that are tuned to see those. Okay? All right. Moving our way up here, I'm now going to go to here to UV. UV stands for ultraviolet. Ultraviolet. Ultra simply means beyond. Violet, we can see. Beyond violet, we cannot see. Ultraviolet. What is ultraviolet responsible for? Yep. You can get cancer from ultraviolet. What is it ultimately? How do our bodies respond to ultraviolet radiation? Yep. Yeah, sunburn or suntan. Okay. Past ultraviolet. Oh, by the way, this is high energy. These are short waves. And we say about all of these guys here, this is, I can't spell it. Penetrating. Is it an I or an E? Penetrating radiation. And that's what you're thinking of when you're thinking of radiation. It's dangerous. Penetrating radiation can be dangerous. What can it penetrate? Our skin, right? Visible can't penetrate our skin. That's how we see each other. The light from the lamp comes and hits you. It bounces off your skin into my eyes. I see you. Josh, I see you. Does that make you feel important? That's a good thing. So I see you because the light bounces off of your skin. But ultraviolet light can get into your skin just a little bit. It's kind of wimpy penetrating radiation. It can just penetrate into your skin enough to burn the skin. X-rays. X-rays. Even more penetrating. They didn't know what type of rays they were, so the guy who named it said, well, let's call them X-rays. X-rays are obviously quite penetrating. They can go right through your flesh, all the soft parts, but they can't get through the bones. So they go through the soft parts, they get absorbed or reflected by the bones, and then you can take a picture of the bones because it's as if the flesh isn't there. But it's penetrating. It can cause damage to cells. If it damages a cell in such a way that its DNA has been altered to cause that cell to reproduce and reproduce and reproduce and grow out of control, what do we call that? Yeah, that's cancer. So all of this penetrating radiation has the ability to be cancer causing. It doesn't mean that every interaction causes cancer. It doesn't mean when you go out and get some UV rays from the sun, instantaneously you have cancer. But the more radiation you are exposed to, the greater the chance of an interaction with a cell, and therefore the greater the chance for that scenario. Yep?
So if you break bones a lot, you have to go to the eye and get X-rays a lot, then you get cancer from it?
No, because they wouldn't give you X-rays anymore. Let's say you had a really bad year, and you went to the dentist, and actually the dentists don't talk to the doctors, but the amount of radiation that they use anymore is so small. So when I was a kid, and if I had an X-ray, they actually had a photographic plate. It was actually a picture that was taken. Now they use digital cameras that can read X-rays. So they can get a good image with just a small little bit of X-ray light, okay? But let's say you had a bad year and you needed an X-ray in January for breaking whatever, and then you broke something else in March, and you did it again in July, and at some point, if they're keeping track, they would say, nope, you've had too high a dosage of radiation this year. We're going to assume it's broke, and we're going to put a cast on it because we're not going to expose you to any more X-ray radiation. They would stop that. Actually, the X-ray technologist, he or she has to wear a badge, right? And the badge actually contains an X-ray absorbing type of device, and they have to connect that to a computer. And if that X-ray technician has been exposed to too many stray X-rays through doing their job, they would actually be removed from the job. They would be given a job working at the desk or something else, and they would not be working anymore because they would then be exposed to too many X-rays. That's why the X-ray technician, puts on the lead vest and then goes, we'll see you later. I'm walking way over here behind this big concrete wall with this really thick glass that has lead in it, and I'm going to push the button now, and then they come back out. Because if they were to be in the room every time, they would be exposed to too much X-rays. So that's why they do that. Okay, X-rays, penetrating. Now for the really, really crazy energetic ones, gamma rays, all right? And in a moment, I'm going to talk about where these are produced. We're going to take a look at how they're produced. We're going to write some stuff down, and then I'm going to show you some stuff about these. Gamma rays are produced by nuclear events. So if you have a nuclear material like uranium, it can produce gamma rays, all right, and it can be dangerous. So what I want to do now, and this is where the world is going to kind of fall apart here with my use of making videos and technology in this. I want to write a little bit of information down about each of these things. So on Google Classroom, okay, and I don't care how you do this, on Google Classroom, and this computer's running slow. I think this is going to fall to pieces. Yeah, terrible. You'll notice that it says here, EMR table document. Open that document up. Now, you can write this on a piece of paper, or you can write this down on the document. But right now, what I want to do is I want to go through the different types of radiation that we did here, okay? I want to talk about where it can come from, okay? And I want to talk about some effects of those radiation, okay? And I was going to show you some videos, but I think I might just show you some of the stuff. So if you want to open that up, and you can type into it if you want, or you can write it down. Now, I was going to show the videos. I'm not going to show the videos. I've got these short little clips of videos, but I'm actually going to just talk about it. So in the first one, put down AC, because we're going to work our way across. And you could fill out whether it's high or low energy. Is AC high or low energy? Low energy, all right? Sources of radiation. Sources of AC are the electricity in the wires. So the wires of our house. So for source, you could put electricity in wires. You want that? Oh, did I actually do that? Yep, I just broke a very expensive piece of glass.
You did?
It's not a big deal. It's for my other experiments. AC, the electricity in the wires. So right now, in all the wires around us, there is electricity, and it is undergoing AC. What does AC stand for? Yep. Alternating current. That means the electricity in the wires are wiggling back and forth, just like in the rod that I was doing. So those electrons in all of the electronics that we're using here is producing light. I can show you a way in which you can catch that AC. Here I've got an old guitar amp back in the 80s when I was a guitar hero. No, I wasn't. I actually was very bad at playing the guitar. Here, I'm going to plug that in. Awesome. You know it's going to be loud, right? When you hear that noise. So, I got to crank right to the top. You can already hear a hum. That hum is this wire catching the AC radiation. We say that that hum is 60 hertz. If you turn up an amp or a radio really loud, you know how you can say it's going to be loud because you can hear that. It'll always be the same. That is AC. If I put my thumb on the end of this, oh, why can't I make it really hum? Oh, it's oh, that's no good. Oh, this amp is old. I haven't done this in years because I haven't taught this in a while. Yeah, I don't know if you've ever done that before where the guitar amp goes. I don't know why that isn't working. Have you ever heard that before when you did that with a guitar amp? Okay. Well, my amp sucks. What's happening is when you touch that, you're becoming an antenna to catch the AC, and all the electrons in your body start to vibrate. And that sends it to the amp, which turns it into sound, and then you go. What is the effect or application? Interference. We call that electrical interference. You've heard of interference before, that type of thing on an electrical device? That's due to AC. If your device isn't grounded properly, you'll have that. Okay, so the second one, radio waves. High or low? Energy. What do you think? Low. In actual fact, by the way, visible is the dividing line, right? Visible is the dividing line between high and low. Sources of radiation. Well, it's electrons, and I'll say this again a little slower for you to write down. Electrons in transmission towers. So write down electrons vibrating or wiggling, electrons vibrating or wiggling in transmission towers. All right? We are writing down in a chart like that on a piece of paper each of these different types of radiation. We're going to talk about the sources and things like that. Transmission towers. You know the big towers that are at the radio stations? They have great big wires in them that the electrons wiggle up and down, and they send out a radio signal. Let me grab here a radio and show you. Okay, so here we've got a radio. And I'm going to bring this. I built this. Justin, I built this solely for you because you were asking about the cells, and I was talking about a Faraday cage the other day, right? So I built a little Faraday cage. So here's my radio.
500 cards for just $9.99.
Classic CHOK radio.
Sure did. I just selected from their template.
In their transmission tower, electrons are wiggling. My antenna is catching that, just like the pith ball, and it's turning it into sound. Radiation cannot penetrate an steel or metal cage. And that's because as the waves come in, the electrons in this wire absorbs all that energy. So if I take the radio and I put it into a metal cage, you got to listen carefully on this. Oh, that failed. Did it get a little quieter? This works great at home. Let me pick a better station. If I misalign it, let's see what we get. A little bit. So there you can see I've absorbed some of that radiation from getting in. Oh, no, I'm stuck. I'm going to dump it over. I tried it with my cell phone. I couldn't get the bars to go down. I was hoping the bars would go down. You always wonder, why do we have no signal in here? Because the studs in these walls they're metal. They're aluminum. So they do the same thing as the Faraday cage here. Okay. Sources of radiation. Did we say that? Yeah. So, radio and television. Our uses, applications and uses. Radios and television. Even your dishes. You know, if you've got a dish, instead of like a TV antenna, you got a dish going to a satellite. Radio waves are being sent to that satellite. Yep. The types of radiation are these guys. Yep. Okay. Microwaves. High or low energy? Low. They are low energy, even though they do result in cooking food by heating up water. By the way, they only heat up water. In a microwave oven, the color of the microwave is perfect that it causes the water molecules to spin around. They rotate. It is only the water molecules that are being heated in a microwave oven. That's why you'll notice sometimes there's cold spots or hot spots. If you've ever tried to make popcorn in a microwave, that works great. But if you've ever tried to reheat popcorn in a microwave, that doesn't work because there's no water left in the popcorn. When you pop it, you expel all the water. So you can't reheat popcorn in a microwave because all the water's gone. Yeah, it makes a mess. Yep. Yeah. Yes, it would. Yep. Yeah, it would. It would. I got to keep going. What did we put? Sources of microwaves. That's a tough one. The device in a microwave oven is called a magnetron, and you can write that down if you'd like. A magnetron. They're dangerous because they produce that right color that would cause water to heat up. If you were to take a magnetron out of a microwave and activate it with you being in the vicinity, you would heat up all of the water in your body, and that would be bad. So very dangerous. Don't play with magnetrons. No, it wouldn't vaporize, but it would heat it up. You'd be heating yourself up on the inside. It wouldn't be good. You'd be cooking yourself from the inside. I don't know how the cell phones produce microwaves, but they do produce those weak microwaves. And I don't know what the little device is that does that. So I'm sorry, I have never looked that up. So let's just go with magnetron. Effects and applications, well, microwave ovens, heats water, that's all they heat, yep. And then obviously put cell phone communication, they also use microwaves. Oh, I wanted to talk one other thing about the radio waves before I get too far. Let's just go back to radio waves. I can actually produce radio waves myself easily in the laboratory. So if I bring this back up, and I don't pick a particular channel, so you can hear there's some noise. But if I have some electrons that would wiggle around, I can produce some radio waves. I happen to have a device that produces all kinds of electrons. This device is called a Tesla coil. Now, this Tesla coil is going to produce lots of electricity, and that electricity is going to be AC. So as I plug it in, do you hear how that thing right away started to pick up on that? I don't know if you can see the little glow coming from the end of it. Can you see it? There's a little blue glow. Now do you see it? All right. That's what you're seeing when you're seeing a taser. This is kind of like a little mini taser. So that's what you're seeing. I'm not doing it. You want to do it? Touch that tap. Oh, it's grounded. It's not working. I have touched it before. It gives you kind of a good little jolt. But notice what happens to the radio. Notice what happens. You can hear it. These electrons are producing radio waves. This antenna is picking it up. What happens if you have a thunderstorm and you're listening to the radio? You notice if there's a thunderstorm. How do you know? Right. That's the same thing. Now, I'm wondering, what if I put the Faraday cage around it? I wonder if I could stop those. There you can see that got quieter. Right? Let's see if we can prevent those from getting in there. Nope, they're too powerful. They're still getting in. That's fun. Oh, my iPad is not enjoying this. No, it's not. And my phone, still running. Beautiful. Okay. In other words, further away? Do we want it in the Faraday cage or not in the Faraday cage? Can you hear it? Put the cage on it. Did it stop it? Nice. So it must be that I was so close that those radio waves were so intense they were able to get past that cage. So again, those accelerating charges over there that are jumping around are producing radio waves. And we were able to absorb them with the Faraday cage. That's fun. Next, infrared. So you're writing down infrared, heat. And infrared is caused by small electron jumps in atoms. Small electron jumps in atoms. I want you to put there as the source. Small electron jumps in atoms. Remember when we did the Bohr diagrams and we put the orbits? Those electrons can jump to different orbits when they're energized. If the jump is really small, like from one orbit to the very next one, infrared radiation is given off. Okay? Applications. Thermal imaging cameras. Does that sound correct? Is that the way you say that? Night vision cameras? Yeah. Put down night vision goggles or night vision cameras. You know the ones that you put them on and you can see the things that are warm. Thermal imaging goggles, night vision cameras, that's good. Scope, like night vision scopes, you can get them for a gun. Whoa, that's cool. And they show you the heat of, say, a deer or something. That's neat. That's neat. That's a use. Okay. Visible. We're now to visible. Come on, folks. Visible. Let's keep rolling. Visible. I'm now at visible. For high or low energy, put medium. It's in the middle. It's right in the middle. It's not penetrating. It doesn't hurt us. Is it like pH that it's neutral? That's an interesting way of looking at it. In terms of its energy, it would be not hurting us, but then the low doesn't hurt us either, right? But it's not like pH. But that's a good connection to it. It's just medium energy. Sources. Medium electron jumps in atoms. Remember I said small electron jumps for IR? These are medium electron jumps. They're not like really big jumps, and they're not like really small jumps. It might be like 2 orbits if it jumped by 2 orbits, right? It's medium as well. It's a middle energy. Application of visible light. We can see it. Our eyes. Put humans' eyes or eyes. We see it. We detect it with our eyes. We can see the light. So next we're doing UV or ultraviolet. And we're still talking about electron jumps. And these are large electron jumps in atoms for ultraviolet. Large electron jumps. And this is high energy. Ultraviolet light has the ability to illuminate glow-in-the-dark substances. Black light, put that down as a use. I actually have a black light. I've never used this one before. I have no idea how this is going to work. Let me show you a couple of things here. I need a piece of paper. So black light is a use for ultraviolet. Let me shut off all the lights here for a minute. I've got a couple of them. I've got an industrial black light, which actually produces radiation that can be dangerous to our eyes. So I'm going to leave this thing on it. And I'm not going to expose you to it. But I've got some glow-in-the-dark objects here. And I've got some glow-in-the-dark powder here, which if I were to put it on my desktop, right there, I've also got a glow-in-the-dark pen, invisible ink. I was going to write a letter or write a something. And let's see if we can illuminate these with the ultraviolet light. That doesn't function. Oh, I need to turn it on. So that's so bright, I don't know if we're actually seeing it. Can you see that that's kind of glowing a little bit? Yeah, that's actually not what we want that for. So I haven't tried that one before. Let's try a different source here. So here I've got a black light bulb that someone has supplied us. I've never used it. Let's see what it does. Let's turn that on. Turn that on. But you know what? It's not illuminating anything. That's a really bad source. So I apologize for that. Looks like my ultraviolet sources are garbage. Yeah, that one's no good. So I apologize. My ultraviolet sources are no good. Don't sweat about it. I thought maybe I could get that to glow, but it doesn't work. I have these UV beads that supposedly change color in the presence of ultraviolet. Let's try my strong ultraviolet source here and see if I can get these beads to do something. So let's hammer them with some ultraviolet light. Actually, you know what I'm going to do? I'm going to leave them on there for a moment. They're being hammered. And I'm just going to get the rest out of the way so I can keep going. So if that is an ultraviolet source, then I'm hammering those beads with some ultraviolet light. And in a moment or two, I'm hoping they change color, but we will see. The source of radiation for ultraviolet, source, large electron jumps. So again, we're talking about electrons jumping, but they're really big jumps. No, they're like four orbits or so that are jumping. Let's see if our ultraviolet beads have changed color here under this. Oh, yeah, that did work. Can you see it? Yeah, one's blue, one is pink, all right? And they were colorless moments ago. So I'm going to put those in there, and we'll gather those up, and we'll take a look at that in a minute. Okay, let's move on. Let's move on to X-rays. X-rays. X-rays are produced by, and so their source is, I'm trying to keep this nice and simple, stopping extremely fast electrons. So just write down stopping extremely fast electrons. So they make a beam of electrons that's going phenomenally fast, and they run them into a piece of metal. And as they stop, they wiggle, and they produce these X-rays. That's the source. Stopping of extremely fast electrons. Applications and effects, medical imaging. Medical imaging, right? Like an X-ray machine. Medical imaging. And I do have an X-ray tube. Right here, this is an X-ray tube. This is designed to produce X-rays. You can see there's a little target right in the middle of it. You see the circular target? And I have actually electrified this with my Tesla coil, imagining, am I sending electrons to that target? And then I thought, if I am, I'm producing X-ray, and that could be dangerous. So I stopped. There's no way for me to detect the X-rays. I don't have an X-ray detector. So I stopped playing with that because I was afraid I was producing X-rays. I'm going to take a look at these UV beads one more time. Oh, look at that, beautiful. See how colorful they are? So they must have a chemical compound in them that responds to the ultraviolet radiation. In actual fact, X-rays would do this too. But I don't know how to put a bunch of beads close to my X-ray producing tube. Okay, last one, gamma rays. Gamma rays. Source of gamma rays. Source of gamma rays. Nuclear decay. Nuclear decay. When a substance like uranium breaks down and becomes it changes. It undergoes a nuclear change. It will produce gamma rays. Okay. Uses of gamma rays. Question? What do you got? You got one? Well, the nuclear bombs contain the nuclear material. They're forced to undergo a nuclear change very rapidly, which causes them to give off vast amounts of energy. The bomb is not designed to use the radiation necessarily as a weapon. It's the energy that's the weapon. But the products of the reaction that are spewed all over the place are highly radioactive and give off lots of gamma rays. So that can also have an effect on the people nearby the nuclear bomb. But it's actually an energy device, not necessarily a radiation device. So yes, nuclear bombs produce them, but let's think of something nicer like radiation therapy for cancer. If you, and we all know someone who's had cancer. We're that type of a situation, right? If they've had radiation therapy, it means they've gone to a machine that produces gamma rays to irradiate the tumor, and the idea is that the gamma rays will kill the bad tumor cells, okay? So that's the idea. It's kind of odd because gamma radiation can cause cancer, but they're using the same energy to try to kill the tumor, okay? If someone has had chemotherapy, it means they're taking in chemicals. The word chemo is the same as the word chemistry, and so chemotherapy is chemistry, and radiation therapy is gamma radiation. Kind of, yes, correct. Now, be careful when watching things like Marvel's, like the Avengers. Everybody likes watching the Avengers, right? And you know how they talk about gamma sources, and they need Dr. David Banner to come and check out the staff of what's his name staff? Loki's. And they're saying, oh, the gamma radiation is off the charts, and how gamma caused him to, because he's a gamma specialist. No, not real. All they've done is they've simply grabbed the word gamma, that is a dangerous sounding word, and have used it. And you know, he uses that little thing to check the gamma radiation of the staff, and he's like, oh, they're off the charts. I'm like, if that thing's producing gamma radiation, you guys should all be, you know, in suits and, you know, protecting yourselves. So be careful with that. Yep. Say that again. In a nuclear power plant, they're using that energy of the bomb in a controlled fashion. And the fuel at the end is also radioactive, just like the bomb. And so they don't use the radiation. It ends up being produced. They use the power to make electricity, but the radiation is from the products. And that's a difficulty because they have to store that. That's the end. I'm going to stop my video there. All right. They're